Today we are going to see how we can convert this grayscale image to this colorized image using a neural network. Of course, I am using Python here. Has it ever happened to you that you have a childhood image which is grayscale or black and white and you want to convert it to a color image? Or you might have images of your grandparents which are in black and white and you want to convert it to colored image. So today we are going to see how we can train a neural network to convert grayscale images to colorized image. First, I am importing the basic elements, then I am activating the GPU. The code I am providing is fine with both GPU and CPU, but note that CPU will require significant time to execute the program. I'll provide a Google Colab link of this file so that you can tailor it for your own projects. For this particular project, I am using Cypher10 dataset that contains 60,000 images of 32 by 32 resolution. 50,000 of these images are used for training and 10,000 are for testing. I'll not use all 10,000 for testing purpose in this video. Cypher10 dataset is a popular dataset and download functionalities are already available with PyTorch. Here is my colorization neural network. This neural network is designed for image colorization, transforming black and white images into color. Inside the init method, we define 4 convolutional layers. Starting with a grayscale image, we progressively transform it through these layers. This conv1 takes the grayscale input and produces 64 feature maps. Conv2 further processes this into another set of 64 maps. Conv3 increases this to 128, capturing more complex patterns. Lastly, Conv4 condenses these down to 3 channels, representing our RGB output. The forward method describes the data flow. The input is passed through each layer and activated with ReLU functions. After the last layer, we use sigmoid to assure our pixel values stay between 0 and 1. We are initializing our colorization net model and moving it to our device, which could be CPU or a GPU. We define our loss function, which is mean squared error in this case. This measures the difference between our predicted colorized images and actual ones. We also set up the optimizer here using the popular Adam algorithm with a learning rate of 0.001. This optimizer will adjust our model parameters during training to minimize the loss. We have a simple utility function, RGB to gray, which converts RGB images to grayscale. It does this by averaging the color channels for each pixel. We'll be calling this function to create inputs for the neural network. The expected or the target output will be the original color image from Cypher10 dataset. We start by setting the number of epochs to 30. This means we will be passing our entire dataset through the model 30 times. If you use the free version of Google Colab, you can set it to 10 because otherwise playing with the code will finish the daily GPU quota pretty quickly and running on CPU will be quite slow. With 10 epochs, I found that there is a reasonably good result. The outer loop iterates through these epochs. For each epoch, we will train all the batches of data. Next, we perform the forward pass. We feed the grayscale images into our model, which attempts to colorize them. We then compute the loss by comparing the model's output to the original images. Following that, we assure that backward pass and the updatation of weights occur. For monitoring purposes, every 100 batches, we print out the current epoch step and the loss value. Here is the monitoring output. Looking at the loss, it seems 10 epochs should be sufficient enough. Anyway, we have the trained model now that has the ability to take a grayscale image as input and create a corresponding color image. In this part, in this particular block, we have several functions that will help us display the results. This ImShow, this function takes a PyTorch tensor representing an image, normalizes it, and displays the image using matplotlib. It can handle both grayscale and colored images. Visualize all three. This function displays original, grayscale, and colorized images side by side for visual comparison. It takes in tensors for each type of image and displays up to n images for the batch. Here n is 5. So we are not really displaying all the images of the test batch. Then we have the functions torch RGB to HSV. This function converts an RGB image to hue, saturation, and value format. This is useful because certain image manipulations are more intuitive in the HSV space. Then we have torch HSV to RGB that converts an HSV image tensor back to RGB format. This allows us to work in HSV space as well, then convert our result back to the more familiar RGB format. We have a function exaggerate colors. This function exaggerates the colors of an RGB image tensor. It does this by increasing the saturation and the brightness value components in the HSV space. This can make colors in an image appear more vibrant. The training images in Cypher10 dataset are a bit blurry since they have a small size, 32 by 32. This function exaggerate colors will help us exaggerate the output color image a bit. This part is for the testing part. This code block performs the task of generating colorized images from grayscale images. The grayscale images are coming from the batches of test data, which are colored images. We are converting them to grayscale images. Then we put those grayscale images as input to the model, and the model returns us the colorized images. Then we are displaying the original image as well as the grayscale image and the colorized image that is returned from the model. We only go up to batch number 10 from 0 to save some execution time. And here is the output. Let's take a look at few of the outputs. For example, let's take a look at this frog image. So this is the original frog image. Note that in the test data we had this original image, but we did not use the original image in the input. Rather, we provided this grayscale image in the input of the neural network, and the neural network returned us this colorized image. This colorized image has more color than the grayscale image, obviously, and the colorized image is resembling toward the original image. Here we have this grayscale horse, and we have this colorized image of the horse, and this colorized image of the horse is matching the original image. Again, note that this original image is in the test data, and the model never saw this test data before. Here is a bird flying in the sky. This is the grayscale image. This is the colorized image. Notice that the surrounding of the bird has the blue sky. And also in the original image, there are surrounding blue tone around the bird. It's pretty impressive given that the Cypher10 dataset has quite blurry images, and we trained on those blurry images. Here is another grayscale shape, colorized shape. Colorized shape has water, blue tones of the water around, and there is blue tones of the water around in the original image as well. So now actually I became interested to see what if I provide a random image from the internet and try to see how the model behaves. So I collected a horse image, which is practically this horse image from the internet. I converted this image to this grayscale image, and I fed this grayscale image to the trained model, and the model returned this colorized image. The grass and the surrounding, it looks like more winter season or maybe late winter season, where the grasses are a little bit dry, a little bit brownish. So here is the original image, here is the grayscale image, and from the grayscale image this colorized image was generated. Even though it does not resemble 100% with the original image, it's still, I would say that it's pretty good. The surrounding has brown green leaves, grass in the area. It's pretty impressive given that the model I trained, that model was on very small 32 by 32 images. Also here you can provide whatever image you have. It can be a black and white image or a color image. So whatever image you provide, this line of code will convert the image to grayscale. So even if you provide a grayscale image, you will be converting it to a confirmed grayscale image. Then basically this grayscale image is fed to the neural network and the colorized version is generated. Then the colorized image is saved into a file, and also the original image, the grayscale image, and the colorized image. All these three images are displayed here. Now for better performance, what can we do? So practically, instead of using Cypher 10 dataset, what we can do is we can collect a huge number of color images, and then we can convert those to grayscale images. The grayscale images and the colored version of those grayscale images can become our training data. So if we have very crisp images, then our neural network is likely to perform better. If you use your own data and this code, let me know how it performed. Thank you and see you soon in another video.